So now we're looking at navigation example number 2. We have a 42 kilometer per hour wind blows towards west 35 degrees south, while a plane heads towards north 35 degrees west at 152 kilometers per hour. What is the resultant velocity of the plane? So we know we've got a plane flying in a particular direction, and we have a wind that's going to be affecting that velocity. So let's get started and draw our diagram. So we start with the wind, and it doesn't matter which one we start with first. We could start with the plane and add the wind to it. Either way works. Okay, so but in this example, because the wind is given first, we'll draw the wind first. So we've got our Cartesian plane, or the cardinal system, directional system here. Oops, not south, that's east. Okay. So the wind is blowing west 35 degrees south. So what that means is from the west, we're going 35 degrees to the south. So we've got our our vector here, and in here we have 35 degrees. And this has a magnitude of 24 kilometers per hour. So we have the x component here, x1, and we have y1. Now we're going to add to that a vector that is going north 35 degrees west. So that means from the north we're going 35 degrees to the west. So if we think of this y as going straight north, then we're going 35 degrees away from that, right up along here. And I've drawn it quite a bit longer because it's quite a bit larger, the magnitude, 152 kilometers per hour. So the magnitude of that vector is 152, and the angle in here is 35 degrees. Okay, as I say, it's always really important to make sure we place our angles at in exactly the right spot. And so we can draw our x2 down here and our y2 right there. One of the things that happens, and I'm just going to clean that up a bit, sorry. Let's see if I can do that. So rather than putting the 35 degrees here, I'll draw it over here, 35 degrees. So we know that this portion is 90 minus 35, which gives us 55 degrees. So we're going to use the 55 degrees, and I've just done that to keep the drawing a little bit easier to see. I could have put my that blue triangle on top of the vector, but it's easier to work with it below the vector for the sake of the drawing. So we have our vector 1, this is our wind, and we're going to find the x component for the wind. And notice that the x is adjacent to the 35 degrees, and so we use the cosine. So x1 is equal to 42, the magnitude of the hypotenuse, times the cosine of the angle, which is 35 degrees. And so we calculate that, and we come up with 34.404, and that's kilometers per hour west. And now we want to do our y component for the wind. And the y component for the wind is calculated the same way, only we recognize now that the y component is opposite the angle, and so instead of the cosine we're going to use the sine. So we have y1 is equal to 42 sine of 35 degrees, and we calculate that and come up with 24.090 kilometers per hour south. Then we're going to look at the plane. And this is our x2. So again, notice that in this instance, x2 is adjacent to our 55 degrees. So we use the cosine again. We take the magnitude of 152 times the cosine of 55 degrees, and we calculate x2 to be and it's 87.184. So 87.184 kilometers per hour, and it's west again. Let's do y2, and y2 is opposite the angle of 55 degrees, so y2 is calculated taking the hypotenuse, 152 times the sine of 55 degrees, and so we get for our y2 124.511 kilometers per hour north. So now we want to calculate our resultant vectors in the x component, in the x direction, and in the y direction. We've got two going north, or sorry, two vectors going west. So these just add together, and when we add them together, we get a resultant vector of 121.588 kilometers per hour west. When we look at our y components, we have one that's going south, one that's going north, and so these subtract, and we see that we've gone further north than we went south, so eventually when we get our magnitude, we know that we'll be going in the north direction. So let's calculate that, and we get a magnitude of 100.421 kilometers per hour north. Now we can actually draw those vectors in, and I'll put them in green, so we know that we've gone 100 kilometers north this way, and 121 kilometers like so. And so you can see that my drawing is a little out of perspective, but my resultant runs right along there. That is my R. And so I need to find the magnitude of R and my direction. So to get R, the magnitude of R, we're going to use the Pythagorean theorem. We've got Rx and Ry. So to find R, we take the square root of Rx squared plus Ry squared. In this case, we have 121.588 squared plus 421 squared, and then we square root it. When we calculate that, we get a magnitude of 157.7 kilometers per hour. And this question is to two significant digits, and so this becomes 1.6 times 10 to the 2 kilometers per hour. Our next requirement is to find the direction, so we're going to use this theta here to calculate it. We've got Ry, which is opposite, and Rx, which is adjacent, so we'll use our tangent of the angle. So the tan of theta is equal to Ry over Rx, and we get theta by taking the inverse tangent of Ry, which is 100.421 divided by Rx, which is 121.588, and when we calculate this, we come up with an angle of 39.6 degrees, and again we're rounding this to two significant digits, so this becomes 40 degrees. And remember that we've gone from the north towards the west, so we would write this as north 40 degrees west. So to close this off or finish this, we would say the resultant velocity of the plane is 1.6 times 10 to the 2 kilometers per hour, north 40 degrees west.